Hello and welcome everybody to our today's webinar. My name is Markus Herdin. I'm head of marketing at Lauterbach, and it's a pleasure for me to be the moderator for today. Together with our partners NanoXplore and SYSGO, we will talk about how to drive aerospace excellence with NG-ULTRA FPGAs, PikeOS for MPU from SYSGO, and the TRACE32 tools. So our focus is how to provide an end-to-end solution in order to innovate in space applications faster and more easily. Let me start with an introduction of the speakers. From NanoXplore, we have Romain Mahou. He's a senior embedded software developer, and he's in charge of the NanoXplore software development kit, covering low-level driver and bare metal environment, and porting and integrating to operating system. He joined NanoXplore in 2021 and has a degree in electrical engineering. From SYSGO, I would like to welcome Amani Kashu. She's a technical product marketing manager with a strong background in data science, industrial engineering, and edge technologies. She joined SYSGO in July 2023 and has a degree in industrial engineering. And from Lauterbach, I would like to welcome Nicolas Delemare. He's a field application engineer and TRACE32 expert, as well as technical manager for Lauterbach Saal. He joined Lauterbach in 2018 and has a degree in embedded systems. So let me briefly go through the agenda of the webinar. Romain from NanoXplore will start with an overview about the NG-ULTRA FPGA family and key facts. We'll talk about software stack, SDK components, and about radiation hardness by design. Amani from SYSGO will introduce PikeOS and PikeOS for MPU. We'll talk about multi-core handling, and we'll also cover the topic of safety and security. Last but not least, Nicolas from Lauterbach will give a brief overview about TRACE32 products and will provide a live debug and trace demo of an application running with PikeOS for MPU on an NG-ULTRA FPGA. Well, I guess that's enough for the introduction, so I would like to hand over to Romain from NanoXplore for the first part.
Thank you, Marcus, and hello everyone. We are now going to talk about NanoXplore. NanoXplore is a French fabless company founded in 2010, which have several radiation-hardened SoC FPGA addressing the space market. The FPGA design is made in France, and the whole supply chain, including chip packaging and PCB manufacturing, is done in Europe. This year, we are really proud to have seen 2 space missions embedding our FPGA. First one was the Chang'e 6 spectrometer, and the second one is the SWOM X and gamma ray cameras. Both missions were based on the NG medium, which is a small FPGA with 35 calots using the 65 nanometer technology. Moreover, ESA certificates the product for spaceflight according to ESCC certification. The NG-ULTRA, which is the big brother of the NG medium, has 500 calots, and in addition to its fabric, it features 4 real-time processors. The product is mostly used for onboard computing, but it could perform plenty of space applications. This year, we released the Ultra 300. As its name suggests, it has a little less than 300 calots, and it is using the same technology, the same nanometer as the NG-ULTRA. The family will continue to grow with the Ultra 7, which incorporates the 7 nanometer FinFET technology in order to boost performances and reduce power consumption. All our products are targeting the space market, and we aim to address new ones like security and defense. Next step will be to use the 7 nanometer NanoXplore design. On this slide, we will focus on the NG-ULTRA target, which is unique in the landscape of space components. It is based on 4 Cortex-R52 from the ARM ecosystem. In addition, you have a large and robust fabric in the same chip, which simplifies the design of new products. All the memory are protected with error correction code, starting with ERAM, flash controller with a TMR support, and the DDR controller which use the Reed-Solomon algorithm in order to protect up to 2 DDR devices. You are now familiar with the NG-ULTRA specification. I'm use the boot process. First core start from EROM and set up a basic configuration in order to give you the capability to boot either from flash or SpaceWire. The BL1 loaded in memory initialize the remaining device like PLL and DDR, and you have various alternatives in order to boot, for example, a bare metal application or a real-time operating system like PikeOS for MPU, or even an hypervisor with dedicated partitions. If you choose the first option, you should use our BZSP. It delivers drivers and tons of applications in order to tame the NG-ULTRA, tame devices like Flash, DDR, SpaceWire, or even FPU. We delivered popular benchmark tools like CoreMark and Drystone to evaluate NG-ULTRA performances, and loader and init application to adapt the BSP to your use cases. We delivered Python and Lauterbach script in order to debug and more. Should remember from first slide that NG-ULTRA is designed for space, but space is really an unfriendly environment, and we are always receiving radiation from the sun and the deeper space. In order to resist to this radiation, we have designed a radar component, but we verify with dozens of radiation campaigns that our analog device like PLL are robust to single event functional interrupt and single event transient. We are robust to single event upset and single event functional interrupt in our FPGA configuration, and even the Cortex R52 is robust against radiation. Thank you for listening, and I will hand over to Amani.
Thank you, Romain. So let me start first by introducing SYSGO, a pioneer and leader in the European market for embedded operating systems. Established in 1991, SYSGO has a rich legacy of over 3 decades in developing sophisticated software solutions. Our core focus is to deliver safe and secure technologies, making us a trusted partner in the certification of safety-critical systems. Since becoming part of the Thales Group in 2012, we have expanded our reach globally, maintaining a strong local presence in Germany, France, the Czech Republic, and the UK. We are dedicated to deliver products that meet the highest safety and security requirements across different industries. Firstly, we have PikeOS, first released in 2003, and PikeOS is a pioneering product in our portfolio, serving as a Type 1 hypervisor and a hard real-time operating system. Its foundation is a separation kernel that enables it to provide robust isolation for critical applications. Next, we have LinOS, our first product, an industrial-grade Linux distribution with long-term support. It's tailored for sustainability and reliability in complex embedded system environments. And most recently, we introduced PikeOS for MPU. This variant is especially designed for lightweight systems equipped with a memory protection unit, MPU. It offers real-time partitioning for MPU architectures, enhancing performance and safety for embedded systems. And together, these products reflect our commitment to enhancing operational safety and security, ensuring that our clients can deploy their applications with confidence. And we offer comprehensive support through our board support packages, certification kits, and tailored professional services, including expert training and consulting, to ensure seamless integration of our operating systems with any IoT devices worldwide. In this slide, we showcase our current positioning in the space sector, and at SYSGO we are deeply involved in several key areas, like platform command and control computers, and here we provide solutions for precise positioning and navigation to ensure that spacecraft and satellites maintain their correct paths and alignments. Second, we have onboard computers and mission payload. Here our systems are pivotal for military communications to ensure secure and reliable data transmission. Also, we manage UAV flight management, and we specialize in safe and secure virtualization for effective partitioning of spacecraft computing resources. And for ground control systems, we support systems like EGNOS V2 and V3 to enhance navigation accuracy across Europe, and we are also part of projects involving the Korean National Positioning System to contribute to its development and refinement. And also we focus on cybersecurity and safety certification studies to ensure that all systems are protected against cyber threats and comply with the highest safety standards. And lastly, we are also working on a new project based on the Dahlia processor developed by ESA. Together, these initiatives highlight SYSGO's commitment to supporting and advancing space technology through innovative solutions and partnerships. Let's move now to introduce PikeOS, SYSGO's flagship product, known for its robust architecture designed specifically for safety-critical systems. It's worth mentioning first that PikeOS supports MMU architecture, and what makes PikeOS unique is that it operates as Type 1 hypervisor and separation kernel. This means PikeOS is installed directly on the hardware, forming a primary layer of security and safety. Above this layer, users can integrate various technologies, leveraging PikeOS to manage and secure their operations. And how does it enhance safety and security? Well, PikeOS employs a concept known as MILS, or multiple independent levels of safety and security. This framework allows the coexistence of secure and non-secure applications on the same platform. With PikeOS, we manage both when and what, controlling the timing and access of operations on hardware, ensuring that tasks are performed securely and efficiently. And it's also worth mentioning that the system can manage up to 255 resource partitions, optimizing both performance and security. It is essential to highlight that PikeOS adopts a modular approach, facilitating the smooth integration of varied software components. This capability enables the crafting of customized solutions aligning perfectly with the unique needs and requirements of different applications. As you can see in this slide, on the lower level of PikeOS, we find the PikeOS microkernel, which consists of a generic part, a CPU architecture-dependent part called ASP or Architecture Support Package, and a platform-dependent part called PSP or Platform Support Package. On top of that, and in the user mode level, we have the PikeOS system software component, which is the first user space application launched by the PikeOS microkernel. It is responsible for initializing partitioning, inter-partition communication, and health monitoring. On top of the core operating system, there we can find the different partitioners. So, building on the robust foundation of PikeOS, let's now move and explore our recent product, PikeOS for MPU, a specialized version tailored for memory protection unit-based systems. So what is PikeOS for MPU? PikeOS for MPU is an RTOS designed for the highest level of safety and security. It is intended to be used on MPU-based SoCs as well as on heterogeneous SoC implementing MMU and MPU clusters. It has the capability to execute concurrently applications with different level of safety and security, so it supports mixed criticality. It has spatial and time partitioning, and PikeOS for MPU shares with PikeOS the same native API, the same customer development environment, which is Codeo, the same SYSGO development and test environment, the same qualification processes, and both operating systems share about 80% of the same code. And for the existing source code that you have, you can easily port it from PikeOS to the new PikeOS for MPU. And due to the nature of not having an MMU, the virtual address management and the ability to run a Linux operating system, of course, is not present within PikeOS for MPU. But it has address space protection, of course, thread management and scheduling, resource management and protection with respect to resources and processing time, health monitoring, inter-partition communication and synchronization, as well as intra-partition communication and synchronization, and I/O device abstraction and access control. Also, it has AMP multi-core processor support. Let's dive now into the main differences between MMU and MPU. MMU, or Memory Management Unit, play a central role in managing memory in computer systems. They are responsible for tasks like translating virtual memory addresses to physical memory addresses, implementing patient mechanisms, and ensuring memory isolation. This capability is in particular useful in larger and more complex systems, like those supported by PikeOS, where the need for efficient memory utilization and isolation of processes is so important. On the other hand, MPUs, or Memory Protection Units, are designed with a specific focus on memory protection and access control. They allow for the creation of defined memory regions with distinct access permissions, ensuring that only authorized processes can interact with specific memory areas. This level of precision in memory protection is valuable in systems where security and controlled access are of critical concerns, characteristics that are foundational to PikeOS for MPU. Since PikeOS and PikeOS for MPU share the same APIs and operate under the same development environment CODEO, transitioning tasks between these systems is streamlined. This allows simply to move tasks from one operating system to another one, and by using the same API, we are able to reduce significantly the learning curve as you can just apply the knowledge that you got from PikeOS. So here, developers can effortlessly scale their solutions and apply their existing knowledge from PikeOS across different hardware platforms, ensuring a seamless adaptation process that accelerates deployment and enhances system robustness. Having explored the scalability of PikeOS across different hardware systems, let's now focus on its advanced multi-core capabilities. SYSGO has taken a significant step forward by integrating multi-core handling into their time partitioning mechanism to address and mitigate any safety concerns that may arise at both the software and hardware level. On the software application level, SYSGO has provided the tools necessary for users to create and implement an airworthiness architecture based on PikeOS. At the OS level or operating system level, several critical safety measures have been implemented. This includes resource partitioning to prevent interference between tasks, time partitioning to guarantee that processes run into their allocated time without affecting others, and fine-grained locking to ensure system integrity. And by the way, PikeOS is the first operating system that achieved a multi-core certification on ZIL 4, underscoring its capability to handle complex safety-critical applications across multiple cores. So, having examined the multi-core support in PikeOS and its benefits in enhancing performance and reducing power consumption, we must also consider the regulatory and safety certification aspects of using such technology in critical environments. So, as we all know, multi-core processors offer many advantages in terms of performance, efficiency, and size. And PikeOS not only embraces these benefits, but also fully supports multi-core architectures, ensuring a wide availability for different applications. However, with the introduction of multi-core systems, new challenges can arise, especially in managing the risk of interference between cores due to the shared resources. This is where compliance to the safety certification standards, such as AMC 20193, previously known as CAS32A, becomes super essential. These guidelines or safety standards provide essential methods for mitigating risks associated with multi-core processors. And by aligning with AMC 20193 guidelines, PikeOS demonstrates its commitment to safety that ensures that its multi-core capabilities meet the high safety certification standards required in safety-critical industries. So moving forward from understanding the importance of compliance to the safety certifications like AMC 20193 or CAS32A, and let's discuss now the specific strategies employed by PikeOS to tackle the challenges associated with multi-core processors. Here, each challenge represents a potential risk in multi-core environments, and PikeOS has developed targeted mitigation strategies to ensure compliance. So let's start first by cache access contention. And here recent versions of PikeOS is addressing this by incorporating cache coloring technologies in order to minimize cache conflicts between cores. Moving to the next challenge, which is memory access contention. And here PikeOS reduces the risk of interference between processes by mapping virtual memory spaces into physical memory spaces in order to safeguard memory access. So next, and in order to avoid interrupt overload, PikeOS implements an interrupt limiter and use time partitioning to manage driver execution during non-critical phases. And in order to mitigate the risk of scheduler contention, the solution was to involve an independent scheduler for each core alongside time partitioning features of PikeOS to ensure efficient and conflict-free core operation. And for the challenge of contention on OS object access, PikeOS is implementing fine-grained locking, allowing parallel operations without kernel object conflicts and ensuring comprehensive partitioning analysis. And lastly, and in order to mitigate issues in inter-partition communication, PikeOS uses specialized IPC mechanisms like sampling or queuing parts that isolate impacts to involved partitioners only. So as we explored the world of certifications, we found out that different industries have their own special rules for safety. These safety rules have been around for a long time and they don't change much. In the world of security, however, things are a bit different. There are many new rules popping up and they are still figuring out how to work best. To handle this, we decided to focus on one main standard called Common Criteria, which is a big deal in cybersecurity. Common Criteria is a globally recognized standard in cybersecurity. We pursued this path and achieved independent certification at EAL5+ for PikeOS, which is the highest possible level for software considered out of context. The certification strictly evaluates the software itself, independent of any system integration. So with that, PikeOS provides robust platform-level security properties, ensuring separation in time and space, controlled information flow, and access control to resources as evaluated under Common Criteria certification. So in this slide, you can see the PikeOS components and their certification state. So you can see that the microkernel is fully certifiable, which means you can provide all necessary documentation, including traceability and coverage. However, if you have your custom board, the PSP needs to be developed with you as customer. When it comes to operating systems and certifiable APIs, we have a certifiable POSIX, and of course, the PikeOS native is pre-certified. In addition to that, for PikeOS, we also provide a certifiable file system and a certifiable UDP stack. So as you can see in this slide, when it comes to certification, we support all major safety standards. And SYSGO has a very long history in certification projects, and almost every engineer of our team has been involved in such certification projects, whether it's safety or security related. And with that, I will hand over to Nicolas.
So thanks, Amani. I will now continue with the introduction of our TRACE32 tools. Lauterbach has been founded in 1979 and provides hardware debug tools. And ever since, Lauterbach has never stopped supporting new debug and trace protocols and interfaces, as you can see on this slide. Our goal is basically to provide all the necessary means to optimize your embedded workflows throughout all the cycles. So TRACE32 is a modular system where you can add modules to enhance your debug capabilities, as shown on the slide on the right. It consists of the debug and trace modules that support every debug and trace interfaces, as I just mentioned before. The tools can be controlled through our PowerView graphical user interface. It's the same GUI for all products and no matter the architecture of your target. And it has been designed to get the best out of the tools. You will see later with the demo some of those features, typically among them multi-core debugging, performance analysis, cache profiling, code coverage, and many more. So next slide, as you can see, there's quite a lot of information here, but what I wanted to underline is that the tools are covering every development phases. So it's basically going from pre-silicon to in-the-field testing, and also you can have and use of functionality safety features that I will show a bit more later. The ARM core side technology can be used to continuously collect runtime information for software that runs on a Cortex-A and ARM-based chips. Please note that what you see here may or may not be implemented on your target device. Let's first start with the ETM. So the ETM is in charge of generating the trace information about the target program execution, as well as the OS task switches. And on the Cortex-R cores, but also on some Cortex-A cores, you will have access to the data trace. So you will have data access information also provided. Next, you have the STM, which stands for System Trace Macrocell, and it enables real-time instrumentation of a software with nearly no impact on system behavior or performance. It requires, of course, a modification of your target source code in order to send information to the trace sink. And lastly, you have the HTM, which stands for AMBA HB Trace Macrocell, and it generates trace information for the traffic on the core side HB bus. The information generated by the different trace sources is merged into a single trace stream and sent to the trace sinks. Here we are mainly talking about two trace sinks, on-chip and off-chip trace sinks. The on-chip one is basically trace data stored in a dedicated on-chip memory or redirected to a system memory. It then means that a debugger, a JTAG debugger, only can have access to these trace informations and decode it and provide you all the necessary means to understand the trace. And on the other hand, you may have an off-chip trace sink, which basically on the NG-ULTRA SoC corresponds to a TPIU, a parallel trace port, but of course it may be serial trace port for HSSTP, for example, on ARM, or even PCI Express trace interfaces. All these IPs allows you to do some trace-based debugging. I will show that later during the demo. It also allows you to perform real-time profiling measurements, and also, of course, code coverage for certification and for functional safety. I also wanted to briefly talk about the mixed signal probe, which is our analog and digital probe. This one is really interesting because, as you can see here, you have two examples. One I2C, which is completely traced and decoded, and also some energy profiling measurements. And this is really interesting because this is completely linked to the program trace flow from the ETM, and it allows you to know the power consumption for all your application. It can also be used to do some more advanced debugging. Basically, you can trigger on a specific state of a signal or even a specific consumption. So functional safety is a key requirement for safety-critical embedded systems. And Lauterbach provides certified tool qualification support kits, in short TQSK. It basically provides everything you need to qualify our TRACE32 solutions. Different TQSK variants prove the suitability of code coverage, debugging, and also instruction set simulator for use in different fields such as avionics, aerospace, medical, automotive, railroad, and in general industrial projects, and reduce your time to market, effort, and costs. We do also have an open API in different languages such as Python and C, and also a lot of third-party tools integration. Basically, I talked about code coverage, and you can easily export code coverage measurements and feed them into your third-party tools to perform code coverage against requirements analysis. So regarding PikeOS for MPU debugging, you can debug the PikeOS kernel, you can debug the kernel startup, you can debug multiple tasks simultaneously, you can inspect the call task of threading threads, you can debug interrupts and exception or drivers, you can also have access to the stack consumption per threads, and so on. With our kernel awareness, with a few screenshots taken from the demo, you can have access to the kernel resources, so the tasks, the threads, and also the system information, the partition information, and also the stack consumption as I mentioned before. So some of the key features for NG-ULTRA, so we do support the Cortex-R cores. It consists of two clusters of two Cortex-R52 cores. It can be debugged either as an SMP fashion or AMP fashion or even IMP fashion, which is not mentioned here, but for the notice. We do support peripheral of display, flash programming, bitstream programming, and trace. As mentioned here, on-chip trace, off-chip trace, and even the timestamp generator from the SoC. So the demo will showcase that you can debug from the very beginning of the target system. So we'll start from the boot ROM in EROM, and then we'll jump to the BL1 in TCMA. and then we'll jump to the application itself. So PikeOS for MPU on core 0 and a bare metal application on core 1. Regarding what's running on PikeOS for MPU, there are several small applications running, even one which is multi-threaded. But the most important one is actually the HDMI demo, which use the fabric. And basically you have some images in Flash, which are loaded into DDR at boot. And then I can use some push buttons on the target board to display the images to the HDMI. And how does this work? So when I push one button, I get the pictures into a frame buffer into the fabric, and then I do have some sort of HDMI configurator, and through I2C, everything is displayed to the HDMI output and displayed on my screen. So as you can see here, typically the main slide of the presentation of the webinar. So now I'm in the EROM. As you can see, it's basically the loading of the TCM, as you can see by the address and by the code. A few windows are opened. Nothing really important, right now. I will just load the BL1 because I don't have any source code for the BL0. So let's jump to the BL1. As you can see here, the symbols are loaded. I can easily debug by setting some breakpoints into my BL1 application, which is supposed to initialize the DDR and the UART and so on, I2C, etc., etc. So I really have access to all the necessary information for the call stack. And now I will let the system boot. So as you can see, I do have also my terminal, which is here, my serial console, which is emulated here directly within Trace32. The bit stream was loaded, the image were loaded, and now when I'm about to jump to PikeOS. So I'm basically in DDR, as you can see by the address, and I'm the very first instruction after jumping to the DDR. So now I will basically show that I can easily go to debug any startup of the kernel. So P4 main, P4, yeah. So we don't have the source code right now. This is why you see those hatched lines. But anyway, you see that I'm now in P4 main, and then my PikeOS has just started. So there are some multi-threaded application which basically does some loops. Nothing really interesting right now. So I will stop and display some features of our PikeOS awareness. So basically we do have here the access to the task list, and I can easily display more details or even the task structure in a few clicks, which allows me to get as much information as I want to perform some kernel debugging, even though this is not needed here. It would rather be interesting on our applications, but I will show that later. Same for threads. As you can see here, another window for the threads. I can see my multi-threaded application, which is called threads. And I can easily put a breakpoint into any function of my applications just by going through the symbols tables. So let's get this one, the main. You can see I do have many views. Here, let's focus on the C code and my loop. And now I will push the button on my target board to display another image, which will trigger the loop. And as you can see, I'm now halted. So it really proves that I can debug a system as complex and as powerful as PikeOS for MPU, like it was a simple bare metal application. As it's still a graphical demo and we are doing a webinar here, I wanted to showcase another cool feature when you don't have any way to do some graphics debugging. You can easily display frame buffers within Trace32. Typical example is here with the 4 image I have. Now let's focus to the multi-core application. So here we are in an IMP fashion, where I do have PikeOS for MPU on the left and my bare metal application on the right. And it's the user choice to define how he wants to behave when debugging. So basically here it's a mirror configuration. Whatever I do on the first instance will be reproduced on the other instance. For example, for the Go here, as you noticed. But I can even do a Go on the left side. And as you can see, the right side will also start running again. And all this is completely hardware synchronized through the CTI, which is a component in the core site infrastructure, which allows that. And is, of course, already supported in Trace32. And when I just unclick everything, everything is just completely asynchronous, and I can debug one or the other completely apart. Now let's move on to the peripheral window, which is always cool, typically used for bring-ups. Here I will play around with the trace clock and the divisor output. Here it will be 100 megahertz at maximum. As you can see here, I do have an autofocus, which kind of tells me the trace clock frequency. And I will play around and show you that I can modify it on the fly and have direct behaviors. So it's typically used for bring-ups to initialize a memory controller, a flash controller, or even a clock subsystem like here. Now let's move to the trace. So everything is already set up. I will mostly focus on the ETM trace flow. As you can see, when I'm doing a Go, it start recording. We have a lot of displays. I won't be able to show all of them here, but let me zoom in here. You can easily have access to all the nesting of your applications. Typically, if on my multi-threaded application, I can have access and I have all the necessary information, threads at threads, which tells me basically what is really happening. Same here for threads 1, 2, 3. I have all the nesting traced, and you can see the timestamp at the very top of the window. We do also have the same for many other information, typically here the task switches. So as you can see, it's pretty much the same graphical view, but here you do have all the task switches that occurred during this recording. All of this, of course, comes to what we can do with the profiling features, and you do have all the same kind of views here, basically all the nesting with all the timing information, and you will be able to get all the necessary information like total minimum, maximum, average time of any function and interrupt you may have in your recording. You also have some other cool column like internal or external, which tells you the time spent within a function or in any subscalls you may have faced. Now let's take a simple example with the, let me check, yeah, stem print will be fine. Whatever, you have two type of analysis, which is the duration and the distance analysis. So the duration will just show you how much time you spent within the function. So here I do have 6 samples, and same applies here for the distance. So typically used for interrupts. If your interrupt is supposed to be called every 1 second, then in one click you should be able to confirm it or not. And the cool thing is that just by clicking on a sample, but I will just show that on another function in a few seconds. Let me just set up everything. Yeah, okay, so that's pretty much it here. Nice. When I click on go first or go last, it will just had a marker, a blue marker that has been placed here, and it basically puts me at the exact occurrence of this timing. And if I suspect something, I will be able to replay the trace using the so-called CTS, which I will show you later. Now let's move on to the STM, which is the other IP we saw when I was presenting the trace features. So STM is based on instrumentation. As you can see here, I do have a code which is generating those messages. So my multi-threaded application is using different lengths of stimuli, and I can play around with all of those software messages. Even a string message will be displayed. So for now, only my long stimulus is enabled, as you can see on the right with the var.watch window. and then I do a go and then a break, and you can already see my long stimulus displayed, and you can also see the string, which is not displayed as a string right now. It will be on the left window, just next to the system trace.list window, and you can see that hello webinar. So you can typically use this to get some instrumentation, but as mentioned before, it has really low or close to no impact on the performance, which is always nice to use. Next will be the coverage. Of course, you can do some code coverage measurements with TRACE32 and this ETM trace. So from object code to MCDC, the method is here incremental. So it means that I will add trace over traces to get an higher percentage of coverage. Basically, based on this trace, I can process it and get direct results for my coverage here related to object code. So let me find my coverage application, which is, I don't see it right now. Maybe it was above. Let me see it differently. So you have always, like the chart windows, you have different graphical views. So typically here, yeah, the complex 4, that's perfect. And you can see that it's completely covered at object code level. Of course, it's best to show object code, and everything is fine, as you can see. So as mentioned, I can easily switch between different metrics until MCDC, which stands for modification condition decision coverage, which is the highest level required for the most critical projects. Let's take something simple here, which is decisional coverage. And you can see that the results are directly updated according to my analysis here based on decision. And with this incremental trace method, I can just increase and trace more in order to get a higher percentage of coverage. So I'm not sure here, nothing has changed as you noticed, but typically you would get higher results because you trace more information and you pass through more functions than before. And all this can be exported into nice reports, either HTML or JSON. As mentioned before, it can be exported to third-party tools. Let's focus here on all reports. So two types of reports. On the left, you do have the classical report, which gives you all the information, assembly and C code, and even the address. So it's a complete report, but it's linked to addresses, and it's kind of a problem sometimes. And there are some type of thing you cannot do with them. So that's what we created, another type of report, which is more like G code, if you know it. And it's only based on C code. There is no address. And it means that you can merge reports between different ELF on different platforms. So this is another type of report which overcome some drawbacks that we have with our classical report type. So now I will showcase the CTS, which stands for Context Tracking System. And this is a really nice feature which allows you to replay the trace either upward or backwards. So if you have a trace, it's like a video, and we do often the analogy of a debug is like a photo at tea time, and a trace is like a video, and this video can be replayed. And this is really useful because it can be replayed on the target, of course, but the best would be to replay this into our simulator. You can save a complete context and replay it into our simulator, which is completely free. And this is typically used if you want to save a real-time context, a real-time bug, and send it to another colleague for analysis, or even just don't take a debugger for the whole day. You can take your own PC and go into our simulator with all the necessary information and replay. So I've just enabled the CTS. You can see some backstep and backstep over button that appeared. And of course, I can do some step in my trace and some backstep, and the CTS will reconstruct everything. So here, I can see that I'm going through my trace either upward or backward. And I can even check for a specific function and go back here. Here, typically target was not reached, but you get the idea. Thank you for listening to me. A few useful links that are displayed here, pointing all the necessary information that you may need regarding what I've shown on my slides. I will now hand over to Amani for the conclusion.
So coming to an end, let's try to recap the key takeaways of today. So we have presented a powerful collaboration between NanoXplore, SYSGO, and Lauterbach for advanced aerospace technology. So first, red-hard NG-ULTRA FPGAs from NanoXplore are specifically engineered to perform under the extreme conditions of space. These FPGAs are engineered to support high level of radiation and extreme temperatures, which are common in space. This ensures that they maintain optimal performance without degradation over extended missions. Next, we have PikeOS for MPU, provided by SYSGO, which offers a secure and reliable real-time operating system environment that adheres to the highest safety standards, which is crucial for aerospace operations. It simplifies compliance with demanding safety regulations, which make it easier for your project to pass rigorous certifications without delays. And Lauterbach TRACE32 tools extend these capabilities by enabling advanced debugging and analysis. This allows developers to identify and resolve issues quickly, reducing development time and ensuring that software meets safety and performance benchmarks efficiently. Together, these technologies create a seamless and integrated platform that enhances your development process. They enable not only faster time to market, but also ensure that your aerospace applications are both powerful and compliant with current and future safety standards. So we appreciate so much your time today, and we are excited to support your ventures into aerospace technology with these reliable, state-of-art solutions.
Thank you, Amani, for the great summary. This brings us to the end of our webinar. If there are any remaining questions, please do not hesitate to get in touch with us. You can find the contact details for all of us on this slide, or just go to the corresponding website. There you can also find contact details or contact forms. Apart from that, big thank you also to the speakers for the very interesting presentation and demonstration. I hope to see you all soon in our next webinar. Thank you very much.